So folks, let's continue along. We now want to look at a very specific type of power series called the Taylor series. So a Taylor series is a series, it's a power series, and it's one where we take some initial function that we're given, f, some real valued function, and we assume that it's infinitely differentiable. What I mean by that is I can take as many derivatives as I wish at some point A. So if I've got an infinitely differentiable function, then I can construct a Taylor series centered at some point A, where this part should look just like what we usually do in the power series that we've already looked at. That's the x minus the point what we're centering at raised to some power. And here we have, these are our CI values, right? Those are the ith coefficients. That's the coefficient in front of each one of those power terms. And the way we generate those coefficients is by evaluating successive derivatives of that underlying function f at the centering point, and we divide by k factorial, where k is whatever term we're currently working at. So here you can see I've gone ahead and constructed this. If you want, this is f of a divided by 0 factorial. If you want, you could write x minus a to the 0th power, but of course that's just 1, so usually we don't write it. Here we've got the first derivative evaluated at a of our underlying function divided by 1 factorial times x minus a, and again, if you want, you could put to the first power there. And I feel like it's not until the second term that you begin to really see the pattern to this. So this was our 0th term, our first term, our second term. We take the second derivative of the whatever that underlying function f is at the point a divided by 2 factorial, and then we take, there's our power term, x minus a to the second power, and we repeat that. I'll let you read the comment on the Maclaurin series. All I'll say is that a Maclaurin series is simply a Taylor series centered at 0. I don't think it warrants a separate name. One of the things we won't really get into in this class is when does a Taylor series of a function f give you the same values that that function f generates for some input value. And I'll let you read through that. I find that this is a very difficult but very essential topic of Taylor series that often doesn't get stressed as much as it should. So many of you, let me just jump to the point. Many of you have seen, for example, if I come down here, you've seen the Taylor series for the sine function, and where we generate it by, each one of these is an x to some power, and we can see those x to the power terms. That's our power terms. We can see this is in this case centered at x equals 0. And then we have this nice way of generating the ith coefficient. But what I actually want to stress is something that I don't feel like always gets stressed enough in initial introductions to Taylor series, and that is we're able to say that the sine function equals its Taylor series, or in this case, Maclaurin series. And you should be questioning, why is that so? Why is it that the sine of x is equal to its Taylor series? And is that always the case? So that's a topic that I'm not going to dive into, but I wanted to point it out to you because I feel like it's one that a lot of people don't fully understand, and I feel like my discussion through here in these 4 or 5 points should highlight that. By the way, sort of a subtopic, and one we'll practice here in just a moment, is that rather than giving an infinite series for a Taylor polynomial, we could go ahead and give a finite series, and in that case it would be called the nth order Taylor polynomial for function f centered at a given value. And I like to think of this as how you will actually use Taylor series in the real world. In the real world, you're not going to work with an infinite series. Instead, you'll use an appropriate Taylor polynomial to approximate your function up to whatever degree of accuracy you want, and you don't want to really go much beyond that. So there are some remainder theorems and such that you can look at in any calc textbook that talk about how many terms would you have to go out to be accurate, to give an accurate approximation for your underlying function up to however many decimal places that you want. So we'll look at that in the next example. So in this example here, we're asked to give the t6 of x, that's the sixth power, or if you like, I guess you could also say order, Taylor polynomial for the function cosine of x. So if we want to construct that t6 polynomial, what we're going to do is we're going to write out the first 6 terms of that Taylor series. And let's go ahead and just say that that's going to be the cosine of pi divided by 0 factorial times x minus pi to the 0th power. That's the 0th term. Plus, then we will take the derivative of the cosine. So remember, this is just our f of a. And the next term is supposed to be our f prime of a for the first term. And so I take the derivative of the cosine function, which is minus sine, and then we evaluate it at a, over 1 factorial, times x minus pi to the first power. Then we take the derivative of that term, and if we take the derivative of that term, the derivative minus, well, so we want our f double prime of a, which we'll find by taking the derivative of the sine function, which will be minus the cosine function, also evaluated at pi, all over 2 factorial, times x minus pi to the 2nd power. If we do the third term, we get plus, when we take the derivative of this term, we get sine of pi, all over 3 factorial times x minus pi to the 3rd power, and I'll continue. What I want to point out is probably something that you've seen before, and that is when we give the 6th order Taylor polynomial, notice that a lot of our terms actually are 0, in that, in fact, every odd term is. If we look at f prime, that's the sine. If we evaluate the sine function at the value pi, that's just 0. Likewise, this term is 0, and finally this term is 0. And so we could actually simplify that for our 6th order Taylor polynomial, t6 of x is equal to, and I'm just going to clean things up here, folks, the cosine of pi is -1. So we get -1, and here we've got the minus the cosine of pi, so that's plus 1/2 times x minus pi squared. And if we take the next non-zero term, we get minus 1 over 24 times x minus pi to the 4th power. And then for our 6th order term, we get, in this case, plus 1 over 720 times x minus pi. Let me scoot over slightly, to the 6th power. And there's our T6 Taylor polynomial that's centered at x minus pi. And we can see that showing up there. One thing that I'm not getting into right now, folks, is how does this Taylor polynomial approximate the cosine of x? If we look at the graph of the cosine of x centered at pi. And in this case, the answer is yes. And in the case of most functions we want to study in this class, the answer is yes. But I don't think that it should be clear why this in any way approximates the cosine of x evaluated at pi. And that's something that we don't really get into a lot when we introduce Taylor series. And it's something that eventually you'll want to explore. So what I'd like to do now is show you graphically what we've just done as we've constructed that T6 Taylor polynomial. So there should be a link for you to click to go to Desmos to see this. Let's scoot this up a little bit so we can see everything a little better. So here you can see in black I've graphed the cosine function. And if I looked at the T0 polynomial, which for us would just be the first term of our T6 polynomial, -1, let's sketch that graph on our Desmos curve. So here we go. So if we sketch that, there is that T0 polynomial in blue. Likewise, here you can see our T2 polynomial, which is just the first 2 terms of that T6 polynomial, and I'll sketch that here. It shows up in green. And we can see that this quadratic is a very good approximation for the cosine function near x equals pi, so pi is right about here where my mouse is, this green quadratic very closely approximates the curve there. We can get a better approximation by looking at the T4 polynomial. This is now showing up in orange, and we can see that it's an even better fit for longer than that second order Taylor polynomial. And here is finally in red our T6 polynomial. I'm going to remove the other three so the document's less cluttered. And you can see that this 6th degree polynomial, which is what we came up with, very closely approximates the graph of the cosine curve with that centering happening at x equals pi up for a while. We can't talk about the radius of convergence for this because it's not a Taylor series, it's just the Taylor 6th order polynomial. But you can see that the red curve very closely approximates the black curve for a large number of x values in some interval around x equals pi. And just for fun, I went ahead, actually, what did I do here? Did I do the 10th? Let me change that, folks. I did the 10th order Taylor polynomial, and I want to show you that one. I didn't ask you to come up with that, but you can see that the work is just longer, not any harder than before. And let me go ahead and sketch that graph there in purple. And you can see that we've got, again, each order for the Taylor polynomial that we go up gives us a better approximation for the curve. Hopefully that gives you some insight as to why we can say that the Taylor series for f of x equals cosine of x very closely, or in fact is identical to the cosine function. So folks, for the remainder of this video, I'll just have you copy down what I've written. But above we gave the T6 polynomial, which you can see here. One thing that's a little bit tricky is I had every odd term was 0. And so one way I could give the T6 polynomial is by taking out all those odd terms. So if I wanted to give a series that would generate just the even terms, oops, there's a typo there, folks, that should be a 2. If I want to give a series that will generate all of those even terms, this series will do so. And you can check when we have k is equal to 0, we'd have 2 times 0 factorial. Let me put that in parentheses. 2 times 0 factorial, which is 1. And the numerator would be 0 plus 1, so we get negative 1 to the first power. So we just get a negative 1 there because x minus pi to the 2 times 0 power is x minus pi to the 0th power, which is 1. So that generates the first term. And then you should confirm that when k is 1, it'll generate the second term. When k is 2, it'll generate the third term. And when k is 3, it'll generate this fourth term because we will have 3 in the factorial expression. Will be 2 times 3 is 6 factorial, which gives us the 720. We'd have negative 1 to the 3 plus 1 power, which is negative 1 to the 4th, which is a positive 1. And then this will give us the correctly powered term. So in general, for any even powered term, we can go ahead and give the Taylor polynomial this way. We wouldn't do it for an odd term because it would just be this plus 0. So this is our Taylor series for the cosine of x centered at x is equal to pi. One thing I'm not going to show in here, but you should be curious about, is why does this actually equal the cosine of x? And it does, but I'm not going to prove it. But notice that this Taylor series centered at x equals pi, it is not the same as maybe the Taylor series you've memorized for the cosine of x, because this was centered at x equals 0, and ours is centered at x equals pi. But both of these have a radius of convergence of infinity, and so both of them are equally good at giving the cosine values. The beauty of having constructed a Taylor series is that it's very easy to incorporate compositions of functions once you've constructed it. So here you can see I ask you to give the Taylor series of the cosine of the square root of x, no longer just the cosine of x. We've got that square root there. But all I need to do is take my answer from above, and everywhere I see an x in that expression, replace it with the square root of x. And that may or may not be easy to compute, but there it is. Here I've got a valid construction. Since the radius of convergence here was infinity, then this in no way inhibits that, except that we require, because of the square root, we require x to be greater than 0. So this holds for all x contained in the interval from 0 to infinity. And so we can, and let's go ahead and call this is our h of x here. So we can give this h of x, which is a infinitely long, not quite a polynomial because of that square root term there, but an infinitely long series that is the same as the function cosine of the square root of x. Continuing down here, folks, I'll just talk through this one. Here I asked you to come up with the Taylor series centered at 0 of this function here. So I went ahead and took the first derivative of this. Notice that if you were to take the derivative of 1 over 1 minus x, most of us, when we're not really feeling 100%, we'll just go ahead and write this as 1 minus x to the negative 1 power and do the chain rule. So we get negative 1 times 1 minus x to the negative 2, and then times negative 1 by the chain rule. So we're left with negative 1 times negative 1 all over 1 minus x to the second power, which is what I've given here. And so I've found f prime of 0. Likewise, I found f double prime of 0, f triple prime of 0, and from there I felt ready to give the pattern that the f sub n of x would be given by this expression here, and when we evaluate this expression here at 0, we just get n factorial. So here I've given the Taylor series for this particular function, 1 over 1 minus x, and here it is. Again, folks, the thing that we're not proving, and you should be curious about, is why does this Taylor series equal this Taylor series for the function 1 over 1 minus x equal 1 over 1 minus x. In this case, I want to point out that we no longer have a radius of convergence of infinity, and instead our radius of convergence is just 1, and so that means that this would only converge for x values within this interval here. Again, as I show in this example, what we're able to do is once we construct a Taylor series, we constructed the Taylor series for this function right here, we can easily compose that with other functions. So here I'm asking you to come up with the Taylor series of 1 over 1 minus 3x as opposed to 1 over 1 minus x, but all I have to do is take my answer from above and replace the x with 3. And that's what I've done here. Here I've given the Taylor series for this particular function. We could also have the discussion, and it is true, that this function g of x equals this function right here. They're equivalent, but this again only holds for a certain interval. Because the interval of convergence for the original function was negative 1 to 1, or the radius of convergence is 1, if I go ahead and replace this with a 3x here, notice what that does to my interval of convergence. And so my radius of convergence has, because we've got this multiplication by a factor of 3 here, my radius of convergence then is 1/3 of what it was before. I say at least here, folks, because it could be under certain circumstances, if you do your tests, these could actually end up starting to include endpoints where they weren't included before. That will not be the case here, but in other instances it may be. So finally, folks, that brings me to the very last Taylor series question that's part of our review, and I'm going to do that in the next video. It's very quick, but I'm going to incorporate it with these other new skills that I need you to know going forward in our class. Thank you.